Let's answer this acid-base calculation question from an old exam. Download the question from the link below and try to answer it yourself first. Don't forget to like and to subscribe and to check out my website www.learnscience.coza. Before we begin, do you understand what a titration is and what its purpose is in a calculation question like this one? If not, pause this movie now and rather watch this movie first. Otherwise, what I'm about to say about this exam question is not going to make sense to you. In this kind of question, the first thing to realize is that one of the reactants is limiting and the other is in excess. That means one gets used up completely. That's the limiting reagent. And then the other one, there's still some left over at the end of the reaction. That's the one in excess. Now, which is which in this example? We're told that HBr reacts with zinc hydroxide according to the equation that we're given, and we're told that the hydrogen bromide, HBr, is in excess. So there's still some left behind after the reaction has completed between the zinc hydroxide and the hydrogen bromide. That means that in this reaction, zinc hydroxide is the limiting reagent. All of it is going to be used up. Why is that important? Because we're asked about the amount of zinc hydroxide that must have been placed inside the flask. That's the same question as asking how much zinc hydroxide reacted with the HBr because all the zinc hydroxide that was put in reacted. So how are we going to find out how much zinc hydroxide reacted? We're going to use the hydrogen bromide to tell us how much zinc hydroxide reacted. How? Whenever you get a question like this, you know that there are three things that are relevant about the chemical that is in excess. What are those three things? Initial amount, final amount, and change in amount. Change in amount means how much reacted. Actually, it's only change in amount that you're really interested in. Why? Because the change in amount of that can then be used via the balanced equation to deduce the change in amount of the chemical that was limiting. Now, we are given information about the initial amount. Right at the end, we're given that. But we're not directly given information about what I could call the final amount or the amount of HBr in excess. That's the reason why we do the titration, to find out how much HBr is in excess. We have to deduce that first from the information about the titration. So we add, in this case, sodium hydroxide. We titrate sodium hydroxide to this amount. And then the HBr now does react completely. We reach equivalence point. Then we stop the titration. And then the amount of sodium hydroxide needed to neutralize that excess amount of hydrogen bromide is what we're going to use to help us deduce, well, how much hydrogen bromide was there actually there in excess. Let's show this with a green line because in this case, the indicator, if we use universal indicator, it's going to turn green as the HBr and sodium hydroxide are neutralized. Then we must stop the titration. That is what they did. And the whole purpose of the titration is to work out how much HBr there was in excess. Okay, so let's put in all the information we know and then let's form a strategy of what we're going to do. We told the concentration of HBr at the beginning, 0.45 moles per decimeter cubed. We're told the volume, it's 90 centimeters cubed. Convert that to decimeters cubed, 0.09 decimeters cubed. So from that, we can then calculate how many moles of HBr were there at the beginning. We don't know the final amount, or let's say the excess amount of the HBr. That we use the titration to tell us. But we do know how much sodium hydroxide and the concentration of the sodium hydroxide that was needed for the titration. Whenever we do a titration, we will know the concentration and volume of the standard solution that we titrate against the solution of interest. So let's put that information in. We're told that the concentration is 0,5 molar, mole per decimeter cubed, and it takes 16,5 centimeter cubed to reach neutralization there. Let's convert that immediately into decimeter cubed. 0,0165 decimeter cubed. Now, also relevant here is we need to know the reacting ratio between HBr and sodium hydroxide. And easy for us, it's 1:1. We see that from the balanced equation. We'll worry about the actual questions that we're asked later. But for now, we're trying to make sense of the situation. From what I've just been explaining, can you see that we can break our strategy up into 3 steps? First, we must use the titration to calculate how many moles of HBr were in excess. After we've got that, we go to the second step, where we calculate how many moles of HBr reacted with zinc hydroxide. Because this will give us what I've called here final amount. You can also call it excess amount. We know initial amount of HBr. Then we can calculate change in amount, which means the amount of HBr that reacted. So this titration is our first step. This change is our second step. Then third, we can see, if we look ahead, that the question actually asks us to calculate how many grams of zinc hydroxide were put inside. And we've already discussed how, because this is the limiting reagent, if we calculate how many grams of zinc hydroxide reacted, that is the same as how much was put in at the beginning. So that's the third step. So now let's do each of these steps. We start off with the titration. So our question is, how many moles of hydrogen bromide must have reacted with this amount of sodium hydroxide? 0,5 moles per decimeter cubed of sodium hydroxide of volume 0,0165 decimeter cubed, and you should write in what we're speaking about, sodium hydroxide. So we can see decimeter cubed cancel. You're left with the number of moles of sodium hydroxide that actually neutralize that HBr. But we need to know how many moles of HBr reacted. And we know that they react in a ratio of 1 mole HBr for every 1 mole sodium hydroxide. We see that from the balanced equation. So then that makes it very easy. Let's get our calculator out. 0.5 times 0.0165 multiplied by 1 is equal to 0,00825, or we can give it in scientific notation. Doesn't really matter. And don't clear your calculator, but maybe to be safe, let's put that into memory A. So we press Shift to recall, which makes it store A. Right, so what does that mean? That is how much over here, how many moles of HBr were still there, unreacted, after the zinc hydroxide tried to neutralize it, but didn't completely succeed. We know information about the initial, and so we can use this initial and final information to then calculate our second step. How much hydrogen bromide actually reacted with the zinc hydroxide. So that's, in other words, the change in the number of moles of HBr, which is equal to the initial number of moles of HBr minus the final number of moles of HBr. Just make sure that it is moles in each case. This one is the final, and that is already moles. But this one here, as I've already indicated, we need to actually do the calculation of concentration times volume to get the number of moles. So that's concentration 0.45 moles per decimeter cubed multiplied by 0.09 decimeter cubed. That's the initial number of moles of HBr minus what we've just calculated. And so let's do our calculation. So you could move things around and actually not clear your calculator, but I think it's simpler if we just use the value that we've stored in A. So let's clear there. Make sure that you do a soft clear, not a hard clear, so that you don't delete the memory. Right, so let's do this calculation. 0.45 times 0.09 is equal to 0.0405 moles. That's the initial, minus recall A. And that gives us 0.03225. What is this? Moles of HBr that did what? That reacted with the zinc hydroxide. Again, we're not going to clear our calculator, but for safety, let's store that into memory B. So we press Shift, recall for store, B. Right. So what have we done? We've now worked out how much HBr actually reacted. But we weren't asked about how much HBr reacted. That's just a tool to help us to find out what we were really asked about, which is about zinc hydroxide. So now we need to make the leap to zinc hydroxide. How many grams of zinc hydroxide reacted if this many moles of HBr reacted? We make use of the balanced equation, and we can see that for every 2 moles of HBr that react, 1 mole of zinc hydroxide is needed. You could obviously simply divide this value by 2, because we know that half as many moles of zinc hydroxide react as hydrogen bromide react. Now, notice that gives us, that cancels away the moles HBr, but it gives us our answer in moles zinc hydroxide. This is how many moles zinc hydroxide reacted, but we asked what's the mass of zinc hydroxide that reacted. So we need to go to the periodic table and look up zinc hydroxide's molar mass, and we find that it is 99 grams per mole, which means that 99 grams of zinc hydroxide is equivalent to 1 mole of zinc hydroxide. Moles zinc hydroxide cancel. Everything cancels except for grams of zinc hydroxide, which is what we were asked. Okay, so I don't even need to recall because I still have this value on my calculator. Divide by 2, multiplied by 99. And we get 1,596. We round off to 1,60 grams of zinc hydroxide. So then we check our questions. We see that this question here answers one of the questions, but one of the questions we have not actually answered yet. And it's asking about the pH of this excess solution of HBr. So we need to work that out. Now, pH is the negative log of the hydronium ion concentration. And we've worked out the number of moles of hydrogen bromide, which is really the number of moles of hydronium because it's a strong acid. And we know the volume, and so we can then work that out here. That's the volume. because concentration, of course, is number of moles divided by volume. So we get our calculator, negative log of 0.00825 divided by 0.09, close bracket, equals 1,0377, rounded off, 1,04. So in this question, we had an acid and a base reacting with one another. One of them, the base, was limiting. And so it was all used up during this reaction. Now we have to find out how much of it was there at the start. And because all of it's used up, that's the same as asking how much of it reacted. How do we find out how much of it reacted? We use the acid that's in excess to help us. How? Well, if we could know how much of that acid reacted, then we could deduce, using the balanced equation, how much of the base must have reacted with it. So how do we work out how much of it reacted? Because the acid is in excess, we need to know how much there was at the beginning and how much there was at the end. And then we subtract. And we find out, therefore, how much of it reacted. Now, we're given the information we need about the beginning, but what about the stuff about at the end? The excess amount. That we deduce from the titration. We perform a titration to tell us about how much there was in excess. And from the titration information, we can then calculate, therefore, how much HBr must have been there in excess. Then we use our subtraction between initial and final to then work out, well, how much HBr actually reacted. And then we use the stoichiometric relationship in the balanced equation between the acid and the base and convert it into grams, because that is what we asked, in order to find out, well, therefore, how much base must have reacted, and since it was the limiting reagent, therefore, how much must have been there in the beginning.